Welcome everyone to the podcast Wireless What, the power podcast that has been organized by the WPT initiative and will be once per month offering you the latest news about these technologies. Today we are happy to welcome Professor Manos Tentzeris, who is a fellow of the IEEE. He received his diploma in electrical and computer engineering from the National Technical University of Athens and the MC and PhD degrees from the University of Michigan. He is currently the Ed and Pat Joy Chair Professor at the Georgia University of Technologies, where he leads the Athena Research Group. Professor Tentzeris has held a visiting professorship at various institutions, such as the TU of Munich, the GTRI of Ireland, and served as anchor guest professor in 2019. He has contributed to the development of many academic programs in areas like 3D inkjet printed RF electronics, wearable electronics, energy harvesting, wireless power, and nanotechnologies. He has published more than 850 papers, 7 books, and 26 chapter books. He's also a member of ERSI Commission D, of the Entity 15 Committee, and of the Electromagnetic Academy, and has received numerous awards, including the 2024 Georgia Tech Outstanding Achievement in Research Innovation Award and the 2019 Humboldt Research Prize. Professor Tentzeris has served in various leadership roles in IEEE and is a frequent invited speaker, having delivered more than 150 talks globally. He has also served as an associate editor for leading journals in his field and has held key positions in organizing and chairing major conferences. So it is our pleasure to welcome Professor Tentzeris to discuss about the emerging technologies in the wireless power field. First of all, Professor Tentzeris, you have an extensive and very solid background in the principles of microwave components, systems, and technologies. What are the main milestones that have you leveraged in the emerging technologies of wireless power transfer to enable zero-power wireless modules?
So it's a very good question. First of all, thank you very much for your invitation. Alessandra, it's always a pleasure to contribute to events like this, raising awareness in a very significant area such as wireless power transfer. I've been involved in this area for more than 20 years, and I would say to make wireless power transfer real and migrate from the preliminary experiments of 1960s to real systems today, a whole convergence of different technologies had to happen, starting from the development of diodes for rectification operating for low power levels, then the development of flexible hybrid electronics that enable the realization of systems that can be conformal. And then I would say over the last 15 years, the emergence of fully additively manufactured RF modules, making possible the integration of all these components together. These technologies, along with the existence and the proliferation of lots of wireless standards, making available continuously increasing power levels, enable either the energy harvesting, so the harvesting of energy that's not intended for wireless transfer, as well as the deliberate wireless power transfer, make them possible. And over the last, I would say, 5 years, all of these technologies coupled with artificial intelligence and machine learning further improve the applicability of these systems. It's very important to list that initially a wireless power transfer was limited to very low frequencies. And I would say till 2010, 2012, the majority of these wireless power transfer systems were utilizing near-field coupling, mostly inductive coupling and sometimes even capacitive coupling. But and the main reason was the existence of off-the-shelf solutions that could be utilized for this purpose. But the problem was the amount of power was not significant, and then the systems were quite bulky. Now, recently, the emergence of millimeter wave enabling the miniaturization of antennas, as well as the proliferation of phased arrays, enabled the wider use of far-field wireless power transfer in tens to hundreds of kilometers and much larger power levels.
Thank you. You have talked about additive manufacturing, and so how disruptive can be additive manufacturing in this field? What are the main exploitations that you have experienced using additive manufacturing, 3D printing, and also we know very original work by you and your group related to a sort of instead of 3D printing, 4D printing. So, solutions that are rapidly changing over time. Can you describe this
Let me
aspect?
share one slide if I can. The main challenge right
Yes,
now for
thank you.
the majority of the RF applications, applications having to do with communication, sensing, localization, cannot be served by the conventional 2.5D configurations. Now, utilizing additive manufacturing, you can have platforms that are spherical, for example, like here, or even 4D or shape changing, adjusting to a variable environments of operation. You can see for most of the systems, there is the famous 5S challenge. That means most of the systems have to be scalable, sustainable, speedy, secure, and smart. And especially for wireless power transfer and energy harvesting systems, as you know very well, the effective area of harvesting or the effective area of communicating or receiving the power is of essence. So utilizing additive manufacturing, you can come up with scalable, highly scalable topologies, such as the tile-based configuration you see at the bottom left. You can integrate this not only in planar, but also in curved configurations like an aircraft or different surfaces. And at the same time, you may integrate very effectively very disparate components, components that are possibly highly directive antennas, antenna arrays, and so on, as well as harvesters that can complement the amount of power you can harvest from RF. So utilizing additive manufacturing, you can have full 3D architectures where you could harvest RF energy or integrate some wireless power transfer topology. And on top of this, supplement with vibration, thermal, and solar energy. So I would say, for example, reconfigurable intelligent surfaces that were enabled by additive manufacturing have revolutionized also the amount of power you can transfer or for harvest. The antennas or the planar lenses that can be integrated with your harvester can allow the harvesting of power from a very wide angular range, enabling effectively agnostic energy harvesting. If you ask me a question about additive manufacturing in 2010 or 2015, when the first RF energy harvesters were developed, then I would say one of the major challenges had to do with the knowledge of the source of the strongest radiation you could harvest, or the direction of the wireless power transmitter. Now, additive manufacturing and 3D printing has enabled the integration of lenses of different types, Rothman lens, Vanata, different lenses that allow the harvesting virtually from all directions, allowing the scale up of the harvested power. You also asked me a question about the 4D electronics.
Yes.
And I would like to show a schematic of a typical 4D structure. This one is a unit cell consisting of subarrays. You can see you have 4 faces. Each one of these faces for the unit cell consists from 4 antenna elements and 1 beamformer. Now, and you have the capability with a very simple folding mechanism, as you can see at the bottom right, pretty much folding and unfolding this to reconfigure the radiation pattern and steer the beam literally to an infinite number of reconfigurability states. So the 4D electronics, or the shape changing electronics, enable you to continuously reconfigure your harvester to accommodate new sources, additional sources, and also different directions, as well as mobility of the platform where you want to harvest. And that's why I consider these near limitless multi-beam radiation patterns enabled by additive manufacturing and coupled with origami reconfigurability could revolutionize wireless power transfer and energy harvesting. And this one can be utilized also in coupling with artificial intelligence. So many times utilizing machine learning or artificial intelligence algorithms, such as this example for deep deterministic policy gradient reinforcement learning, you can a priori reconfigure your phased array to optimize the harvesting capability, as well as to reconfigure the directions where you want to transfer your power without interfering with any other additional components.
Thank you. And what is your viewpoint with respect to keeping all these such incredible reconfigurable systems energy autonomous? Do you think that
can you say that again, because you broke off?
Sorry, my question is, how do you think that these incredibly reconfigurable possibilities can be coupled with the concept of energy autonomy? So you think that they will be self-sustainable, or do you think they need some support?
This system here, as I told you, is realized by minimal power. That's why I stress the term origami, because origami, I mean, for most of the people, origami tessellation is just art and decoration, but the fundamental feature of origami is you can reconfigure the shape with the minimum possible amount of energy. So you don't need any significant energy, pretty much. Just pulling one corner of this unit cell with a very, very low energy motor can achieve a very effective reconfigurability and also stability in the new state. So it is absolutely possible for this to operate just by harvested ambient energy. The amount of power is really, really low to perform that.
Thank you. And do you think these energy harvesting solutions can meet the goal of being sustainable, environmental friendly, and pervasive at the same time?
You are touching 2 very interesting points, Alessandra. Really appreciate. Now, you asked number 1 about sustainability, and I would say energy harvesting helps inherently about this direction, because energy harvesting aims in eliminating batteries whenever possible. So as a first step for IoT devices, it eliminates effectively the need to change millions or billions of batteries. Now, at the same moment, still energy harvesting has not been extensively utilized. So it's important to think in terms of e-waste. And for this, there has been a very significant amount of research in the area of something we call transient electronics. Electronics that can be realized utilizing materials with on-demand biodegradability rate. And what I mean by that, there have been even preliminary demonstrations of electronics on wood or utilizing biodegradable conductors that can achieve quite close performance to the conventional harvesters, especially for low frequencies. I mean, higher frequencies, maybe let's say above 28 or 40 gigahertz, it might be challenging to utilize these biodegradable materials because their loss performance is not extremely low. So typically these biodegradable materials have a loss tangent of like 0.1 or above, which is much more than the typical 10 minus 3, 10 minus 4 loss tangent you typically utilize. But already coupling the harvesting capability with these biodegradable materials, it's a major step to perform sustainability. And on top of this, the capability of coupling harvesters with AI algorithms to select the best frequency bands to harvest or the best shape to collect the energy reduces the number of the harvesters you may need. So a third level of sustainability is you don't need lots of them anymore. You need a small number that can operate smartly with very low internal consumption and actually maybe with a priori design algorithms or configurability algorithms using AI, and still you can do your job. So I would say for these three reasons, definitely energy harvesting could help a lot on sustainability. Now, if I can go a little bit higher, one of the questions typically coming, and I know your research group is one of the leading groups as well on energy harvesting, as well as Nuno's group. We're all aware. The first question that comes up quite often is, what is the amount of power you can harvest? So are you limited to tens or hundreds of microwatts, or can you push it higher? Because you know the typical ambient energy is going to be like minus 5 dBm, minus 45 dBm, minus 50 dBm, sometimes minus 55 dBm. But the use of printable lenses, such as this one shown here, allows now to harvest about 20 to 30 times more harvested power. And that means that it is doable to realize some harvesters that can harvest milliwatts. And then by scaling them, utilizing additive manufacturing, you can go to tens to hundreds of milliwatts. And then you are talking about really practical systems for a wide variety, contributing in an additional way to sustainability and zero power operability.
Thank you. And when you reach these very important and future goals, what are the main fields of application that you foreseen will have a lot of advantages of these energy harvesting techniques? In which field? We know that we talk about smart cities, smart agriculture, smart health. Do you think these fields of application will take advantage of these technologies and of this, the optimized version of these technologies?
I will show an example from 2010. That's how it all started.
Ooh.
So that's some collaboration of our team with University of Tokyo for smart agriculture. So 2010, we realized some smart agricultural sensors shown here. That was on paper. That was photographic paper. Here there were two sensors: soil moisture, leaf wetness sensor. And then if you look at the right, there were two antennas. That was a long S antenna to harvesting energy from the local TV station, and a shorter monopole at the top right, which was transmitted to the gateway. So that's how it all started. Really, devices with minimal consumption being utilized for a smart house, utilized for precision agriculture, utilized even some preliminary forms of Internet of Things. Now, where we stand now, and if I can look backwards, is here. So now, this is the Internet of Smart Skins, and this one can find applications to quite a wide variety of platforms, ranging from smart cities, ranging to pretty much autonomous robots or cobots, as we know, and going all the way to digital twins. Over the last 10 to 15 years, we have seen a transition of the interest from single units, single tags, single modules, to constellations of modules. So right now, we're trying to take advantage of the numbers. Instead of having only one device that would be utilized for some plants or to monitor some detrimental gases for smart city applications, now we're talking about tens, hundreds, thousands, millions. And that has led to the first real applications of digital twins. So digital twins is pretty much some digital representation of the real world. And there were lots of roadblocks. One of the major ones was the energy. To have some accurate enough digital twin, you need millions or even billions of autonomous devices. Devices you cannot change the batteries the whole time. And I would say this is the most important application enabled by near zero power energy harvesting or wireless power transfer enabled devices here that can work effectively. These are devices that are thin and flexible, so they can be integrated pretty much with any object or any platform you have. They consume lots of power. They're batteryless, but still they have three major challenges. And we have to keep that in mind. I would say for everybody watching this video cast, we have to keep in mind, we have energy harvesting. And there are different frequencies, different implementations for energy harvesting. Some of them conventional with use of diodes, some of them utilizing meta-harvesting unit cells. But for all of these cases, range has to be realistic. So for digital twins, ranges of like 5 to 7 meters are not enough. You need to have ranges that are long, because otherwise, the number of digital gateways required becomes prohibitive. Now, we have to keep in mind that even if you have the best zero power sensors, the best RF designs, if you have to place a reader every 5 meters, nobody's going to do it, even if they're autonomous. So we have to find ways. There is a long range, maybe 250 meter plus, localizable in real time, and then being able to be mounted pretty much on every platform: metal, human body, water-based or liquid-based solutions, as well as the conventional platforms. So let's keep that in mind. And that's what's happening today. So We migrated for a single or a small number of autonomous devices enabled by energy harvesting now to constellations. Still, if we look in the future, because I guess for people watching this video cast and maybe getting interested in the area of energy harvesting or wireless power transfer, they have to know what are the needs of the future. And I feel the needs of the future are going to be even more challenging than what we have today. I have this slide here talking about the applications of the future, and I would group them together in 4 major groups that we may have to use as many as possible battery system. One is multi-sensory enhanced reality applications, virtual reality, augmented reality, all of them. So can we utilize energy harvesting to power on devices that are practical and wearable and easy to use? Number 2, smart manufacturing. Industry 4.0 is getting more and more important. And talking about smart manufacturing, it's a whole new system of constraints for the energy harvesting devices. Typically in smart manufacturing areas, or as we call in meta factories or industry 4.0, there's lots of power, but we have to make harvesters that can operate under rugged conditions. So lots of vibration, lots of noise, lots of blockage, and so on. Is it possible to do that? People will need to do that. Then wireless brain-computer interactions or brain-machine interface, and then distributed ledger technologies. And if I could summarize in one sentence what are the challenges of the future, would be the following. Now we're talking about autonomous communication nodes, autonomous sensors, autonomous localization device, but in the future, we'll have the quintuple convergence. Convergence of communication, sensing, control, localization, and computing, and operability literally everywhere. So integrated terrestrial, airborne, and satellite networks. Still, we have one major advantage, one new weapon for energy harvesting we did not have before, and that's the large intelligent surfaces. So more and more of the implementations of the harvesters can be realized on glass substrate or transparent. So you may utilize now large surfaces as the harvesters, surfaces that could not be utilized some time ago, but now the tools are there. And also the diodes are there, and so on. And then also another important point I would say for the energy harvesting is how can you do more with the same amount of harvested power? And that's how we have to start thinking in terms not of areal, but volumetric spectral energy efficiency, like bits per hertz, per joules, per meter cube. And that's a very good metric to shoot for the future.
Thank you. This is a very important point and also original viewpoint of these aspects. So with this in mind, do you think that the millimeter wave spectrum will be a feasible spectrum for the future systems of energy harvesting, considering also this volumetric figure of merits?
We discussed before about an example for, let me focus for this one. So these are tile-based designs you may utilize for either directive wireless power transfer, or every tile could be a harvester. Now, talking about millimeter wave, you have 2 conflicting mechanisms. One is antennas become smaller, and you may realize phased arrays with many, many elements, like massive MIMOs. On the other side, the propagation loss is significantly higher than the lower frequencies. So here, there's a trade-off. But the capability of additive manufacturing to realize very scalable, large arrays made by self-similar tiles or self-similar harvesters makes it possible. So the gain wins over the significant attenuation of the signal, given the fact that the radiated power from millimeter wave base stations like the 5G 28 or 39 gigahertz is much higher than LTE or lower frequencies. Typically for 5G base stations, the maximum allowable transmitted power is about 75 dBm. I would say already the preliminary implementations, they are 45 to about 57 or 60 dBm. And that's a significant amount of power. So reviewing the state of the art and some of the latest experiments we have performed, and I'm sure you have performed similar experiments, the values, the ballpark values now we get from for a credit card size harvester at 5G millimeter wave frequencies is about 7 to 8 milliwatt. Integrating the printed lens we discussed before. Now, there is a caveat here. It's not just the harvester, but also there is the lens. And this lens allows to harvest power from different directions. So I would say now some printed planar lens or integrated metal lens, again, 3D printed or inkjet printed, should be an important part. If we integrate this, which is now miniaturized because we're talking about millimeter wave, this 7 to 8 milliwatts per credit card size is not something insignificant because you may have lots of them. You're not talking about devices that operate with 200 microwatts on and maybe 100 nanowatts off. That was the target 5 to 10 years ago. Now with 7 milliwatts and maybe utilizing 8 tiles, 8 harvesting tiles, you can go to 50 milliwatts. That's a good number. And then if you want to utilize large reconfigurable surfaces, redirecting radiation to the direction of your harvester, again, you can pump up more and more. So I would say millimeter wave is a good alternative. Is it going to be the only solution? Possibly not. I mean, typically to have some pretty much consistent amount of power, in my opinion, you need to integrate multiple harvesters and also harvesters that harvest over different bands. So I would say millimeter wave would harvest a very significant amount of power, and then utilizing even lower frequencies, harvesting fundamentals and maybe harmonics would complement that to come up with some real amounts of power.
Thank you. So you have shown some very interesting and broad scenarios of application of the integration of the energy harvesting modules and, for example, 6G, 5G and 6G solutions. So from your perspective, do you think that the energy harvesting or wireless power transfer with these kind of solutions will be really an emerging technology, an enabling technology for the real exploitation of 6G?
Going back to the needs of 6G, this is an example of some prototypes for 6G that have been reported recently beyond 5G or 6G. And as you can see here, you are talking, first of all, of exploitation of sub-terahertz frequencies. So now we're really getting to D-band or higher. 95 gigahertz, 150, 200 is going to be the first step, and maybe going all the way up to 3 terahertz. Low latency and terabit per second. So requirements are quite stringent, and the loss is going to be stringent. On the other side, additive manufacturing is capable, and it has demonstrated. I don't know if I have some example here. I would really like to show something if I have it in these slides. I don't have it here, but what I want to show was we recently demonstrated fully 3D printed pillar arrays with spacing of 1 micron and maybe 10 by 10 pillars next to each other, which means additive manufacturing is slowly is catching up. So devices all the way up to 200 gigahertz are becoming cheap. So you can print them with a 3D printer. That means you're going to have the scalability. Power level, it depends on the electronics. I mean, one of the big question marks is, do we have the diodes with good sensitivity in these frequencies? That's something to be seen. And I would say lots of work needs to be done on this if you operate in frequencies above 100 gigahertz. Then talking about the integration and materials, as we said, you can realize harvesters now on very low loss, smooth materials like glass. So surface roughness is very small, and that means you don't have any substrate loss. And with the smart selection of available bonds, possibly we could start seeing some harvesters pushing in this direction. I would say, in principle, the millimeter wave harvesters can be extended at least in D band. The main roadblock, in my opinion, is the lack of high sensitivity diodes operating up to these frequencies. And maybe that's something, some great area of research to do that. But the principle and the fundamental parts and the really miniaturization size of the components would make it possible if we had diodes.
Thank you very much. I think we have covered a lot of aspects related to far field energy harvesting, and for younger people that are following this podcast, I would like to ask you, what do you suggest to follow for the next step of wireless power transfer in this field?
As I said in the beginning, and let me share the first slide, because I would say this slide is pretty much the slide that will dominate everything for the future. This is the big 5S challenge. Realize zero power, environmentally friendly, fully additive manufactured components that feature high speeds and that are sustainable. So this challenge will be around for I would say, the decades to come. Maybe the metrics will change. Maybe we'll go from gigabit per second to terabit per second, or we may go from microwatt operability to lower than this. But my advice for young engineers attending this videocast is get involved with energy harvesting and wireless power transfer systems, because that's a very disruptive technology that will make lots of new applications possible. And there are different challenges. There are challenges starting from electronic components. We refer to diodes, we refer to low-loss electronics, for those being interested more in electronics, to integration. So what materials you're going to utilize? What is the shape of the platform that will help you harvesting the energy smarter? And then there are aspects having to do with the antennas, which means the energy acquisition components. And then for engineers being interested in packaging, that's another very interesting topic. how you build enclosures that are mechanically stable, even rugged for environments like Industry 4.0, but still enclosures that do not affect your harvesting efficiency. And then if you move to two higher levels, let's say for people watching this, but are not interested in all of these components or even all this module, think about how you could have even some collaborative harvesting. Everybody is talking about constellation of IoT devices. So can we arrange even the orientation of the harvesters in the appropriate way to harvesting most of the power at the most convenient bands? And then the second higher level I told you, let's think in terms of applications. We talked about digital twins. Digital twins is the holy grail right now. There's going to be tremendous amount of effort within the next 10 plus years to come up with ways of establishing some cyber-physical equivalent of the form of digital twin for growing sizes. Right now, we don't have digital twins than more than like 5 machines. So soon the need will grow in parallel with the need of higher data rate. And then on the other side, the situation will be even more challenging even for autonomous cars. Because autonomous cars, obviously, in my opinion, energy harvesting will not be sufficient for autonomous cars. Maybe for some simple cases where you can integrate coils under the highway in massive scale, that would be possible, but I don't think it will happen soon. So, but still, cars now are like moving computers with very stringent latency requirements. So finding ways to charge even some parts of these autonomous cars and enable just the communication systems, the V2X systems, as we call, like vehicle to everything around this, is going to be another major area of interest. And the last, I would say, grand challenge, would be to think about this convergence of communication, robots, that require not only communication and sensing, but also micro-localization. That's another class of systems that may require to be zero power. How you can enable all of this mass number of robots and cobots to be localized with sub-centimeter accuracy level. So lots of different challenges, lots of different areas. I would say we're still seeing only the tip of the iceberg. So I'm sure within the next 10 to 20 years, we'll see lots of magnificent things. And people may even laugh to our developments the same way people laugh today about the first computers in 1950s. So really exciting area.
Thank you. Thank you very much. It was a very and broad perspective, and I think you will be of inspiration for our interest people in this podcast. Thank you very much.
Thank you very much, Alessandra. Really appreciate the questions. Were really creative and leading to very good points. And I wish best of luck to this initiative for WPT. I'll be happy to assist in future events. And also, I'll be happy to answer questions to all people watching this video in the future.
Thank you. We will announce the next episodes very soon. And yes, it will be a pleasure to have you with us in this. Thank you very much.
Thanks, everybody, and have a great night.